Okay, a little interlude here. Now that we've seen all the basic objects and the relationships, you've got these basic objects, models of convergence and divergence. You've got the arrow relation. You've got functions and arithmetic operating on them as you would hope. And you've got a way to rigorously define everything as far as you would like to. What are the benefits of this approach? I think the first benefit is you get a brand new object of study, and this has lots of aspects to it. The first is that the students get some sort of excitement. It's something new and visual is the core concept of calculus. Something new to study, a new object. You don't get new objects very often in high school to early college mathematics. There's something new to think about, and it sort of sets a new mindset. They move. They're interesting. They're visually, I hope, a bit more enticing. I hate to think that a student would take some number of years of math leading up to calculus with algebra and variables and numbers. They get to this magical field of calculus, and they don't get anything new. There is something new. These notions of convergence and divergence are what we're studying, and we should give them to the students as sort of playthings. Second, and equally important in some way, the fact that there's a new set of objects means there's a natural reason to say, a natural place to say, equality we don't talk about for these objects. Equality is for numbers and variables and expressions in the classical sense. These objects don't sit still, so equality we never use. Happily or unhappily, cancellation and algebra also do not apply. Infinity minus infinity is not zero. You can't cancel these. You can't do algebra. All you do is you plug in, you simplify, you apply functions, arithmetic, and you work with them to simplify your answers. If it doesn't work, as I said before, you simply go back to your original expression in variables and numbers, your original function, and change the way you've expressed it. Use your laws of algebra. Then plug in again and try and get a more precise answer. So again, not only are they exciting because they're new and visual, they also give you a really good place to say, look, 0 times infinity is still 0, but 0 plus times infinity is a different ballgame. Second, they allow us to say exactly what we mean and to see everything. With the introduction of the dot and an explicit meaning for plus infinity, everything has a very concrete realization as an object that they can see and explore and understand. None of it's in any way a misrepresentation. Nothing's hidden. Whatever's complicated mathematically comes out complicated with these because it has to. The math doesn't change. But there's a way to see all the inner workings rather than thinking about numbers and limits and numbers and limits. These squeezing things that are converging towards the limits are what you're studying. And when things diverge, there's still something there that's diverging to see. Also, I've mentioned this a few times in the definition of the arrow relation. These objects operate at both levels. Even at a pre-calc level, a student can see what 1 plus means and see what 2 plus means and reason out and think about these objects and gain an intuitive understanding of them. Once that's understood well enough and you get to the quantifiers, everything you've learned intuitively directly translates into the quantifying for alls and their exists and if-thens, and there's a way to see the definition at work in all of the inner workings rather than just memorizing it. Also, this monotonicity of the squeezing, it really does decomplicate some tricky cases. These jump discontinuities or oscillating functions or indeterminate forms or Dirichlet's 0-1 function, all of these things that typically are stumbling blocks for students, everything can be seen and everything happens monotonically. And that really simplifies all the considerations. And again, it's not a lie. Everything that's said here comes straight off the definitions. Also, I think equally importantly, convergence and divergence. Limits of 2 and infinity, are really 2 plus minus dot and plus infinity. And they're apples and apples. They're not apples and oranges. You never have to leave category to do a computation or leave category to think about these. Nothing's a number. Everything's squeezing in general. That's the sort of thought process I think that the students need to foster, or we need to foster in the students. Finally, this is an issue that came up among some people at the talk. I can't stress this enough. Everything that you do when you write down a formal logical definition of anything we've said here and anything we will say gives you back exactly the standard logical definitions. So the question of whether something can go wrong with a complicated function or an indeterminate form or whatever is kind of a moot question. It can't go wrong because there's nothing different logically. If you unravel these objects, and there's a lot to think about and see in them, but if you unravel them, you arrive at exactly the same logical definitions. We just get a much more clear, sometimes concise, and certainly more robust way of thinking about them and saying them.